Hello, I'm Faraz Syed, and the topic of my presentation is van der Waals nano electronic devices. So today we would like to discuss the interlinking of van der Waals heterostructure with high K dielectric oxide in the development of electronic devices that boosts the performance and as well as they reduce the size of the nano electronic devices. So the contents which I would like to discuss would be how the van der Waals heterostructures are organized and discuss how we can bring the revolution in the field of nanoelectronics, and what is the importance of dielectric constant in the development of nanoelectronics devices. We would also like to discuss the optoelectronic devices. As you know that optoelectronics devices, it is a study that links with the study and application of electronic devices and systems that source, detect, and control light. It is considered as a subfield of photonics. We will also discuss the nanoelectronic devices. We will also discuss the filamentation process. As you know that the filamentation process is a process which acts upon the dielectric breakdown. Electrically conductive filaments are formed. The filamentation process can be used to electrically contact encapsulated conductive material. Careful control of filamentation process also allows for reversible switching memories. We would like to discuss the two-dimension field effect transistor, transition metals, dietical cogenites, and why the atomic layer deposition is not beneficial in the future development. We will also like to discuss the ReRAM devices. As you know, the ReRAM devices are the resistive switching random access memories. And then we will conclude that how our work was beneficial for the future work, and then we will discuss that how this high K dielectric can play an important role in the development of devices that will help in the flourishing future. So starting with the introduction, I would like to know that how the high quality of native oxide plays an important role, how it reduces in the reduction in the dimension of nanoelectronic devices, how it boosts their performance, and what is the importance of fluorescent van der Waals heterostructure devices such as light emitting quantum wells, vertical tunneling transistors, photovoltaic and memory devices are created. And we will also, as you know, that boron nitride plays an important role, how it's used to what is the use of boron nitride, and then we'll compare with do the comparison with silicon dioxide, and why common deposition techniques are not useful. So the high quality of the native oxide that can be grown on the surface of silicon has underpinned the wide success of modern micro and nanoelectronics. In the recent year, you know that fluorescent has been important development, and it helps in the development of much faster nanoelectronic devices. If we compare with the silicon van der Waals structure, are likely play an important role because the multitude of possible heterostructure combination available will allow for device with unprecedented functionalities and improved performance. So, contrary to the conventional molecular beam epoxy growth of semiconductor devices, van der Waals heterostructure made it possible to produce sharp interfaces between the different materials, so they can like to improve their performance. Now we will also like to discuss the interlinking of the fluorescent with van der Waals heterostructure. We would like to discuss that how we demonstrate a root embed ultra thin fluorescent in the van der Waals heterostructure using the hafnium sulfide. You know that hafnium sulfide is a late semiconductor which has a indirect band gap of around 2.85 electron volts in its bulk form. And we also discussed that we found that we will use laser light for the for the hafnium sulfide, and when the hafnium sulfide is embedded within complex heterostructure in the metallic context, this fabrication technique is very beneficial, as it avoids the need of invasive sputtering, or we can say that it avoids the atomic layer deposition method. And there are many applications of suitable dielectric devices that range from field effect transistors, resistive switching, random access memories, vertical light emitters, and photodetectors. Now I would like to discuss the photo addition of hafnium sulfide. We will discuss the experimental setup. What are the effects of laser irradiation, how the laser light plays an important role in the development of dielectric constant, and then we will compare of the comparison of laser irradiation effects in vacuum and atmosphere. And as our experiment has told that how what the similar effect have been observed for graphene on silicon dioxide. So we will also discuss the energy dispersive X-ray spectroscopy, which is also known as EDX. So I will start with that in a way that how that by comparing the laser irradiation effects of hafnium sulfide in vacuum and atmosphere, we show that this process relies on the presence of atmospheric water and oxygen. Furthermore, the oxidation process is still found to occur even when the hafnium sulfide is sandwiched between the neighboring two-dimensional materials. As we now will discuss the image that the figure, as you can see that figure 1a is showing that how the contacts have been defined by electron beam lithography. The desired region of oxide is selectively irradiated using visible laser light. Figure 1e shows that how the process relies on the presence of atmospheric water or oxygen. Now, figure B is showing the STEM image of showing a cross section of fluorescent acid. Figure C is showing the how the optical image of a graphene hafnium sulfide heterostructure. What are the before and after effect? Figure D is showing how the current, so the source to drain current versus applied voltage encapsulated between the boron nitride and graphene. Figure E is showing the optical micrograph. Figure F is showing the two-terminal resistance versus the gate voltage of a graphene. Now I would like to discuss the breakdown of the fluorous acid. The how we do is to do the breakdown of the fluorous acid. It plays an important role, like the breakdown of voltage of the laser written oxide was we used to measure it with the help of graphite. Tunneling current, we used to find the tunneling current, and the tunneling current is according to the Fuller-Nordheim tunneling model, and the tunneling of current was helps to determine as the flux, which is around 1.15 negative in electron volts, which is likely related to non-stoichiometry of the amorphous oxide. So as this diagram is shown, that we can just showing the breakdown of the fluorous acid dielectric. As you can see in the image, E is showing the drain current from source to drain and the voltage from source to drain, and the characteristics of a 5 nanometer graphite fluorous acid. On the top left inside Fuller-Nordheim tunneling model. And the bottom right on the B image B, I can say that we can are showing that what is the current source to drain current and the voltage of source to drain for the extended voltage range, showing the breakdown field of the dielectric. Now, as you know that how the fluorous oxide in electrical contact and gate oxide in dual gated graphene X. So this diagram is a clear concept as the image is showing the source to drain current and voltage from source to drain that indicates the formation of a conductive filament in the oxide, which is shown in the red curve. Further, it reduced resistance to the 10 kilo ohm level, which is shown by blue and black curves. And as you can see on the image B, that we have different values of voltages from minus 60 to plus 60 volt. And the image C is very, as you are familiar with it, it's just like a contour map between the contact 8 and 10. Will contact 9 and 10 acting as a top gate electrode. Now, how the fluorous acid in two-dimensional field effect transistor acts. So, now starting from it, I would like to discuss the drawback of graphene field effect transistor. That in the absence of a band gap, which prevents the use of the single layer of carbon atoms in practical, the current ratio is required. In contrast, few layer transition metal dichalcogene are semiconductor, and because they are atomically thin, they are ideally suited for transistor application. We will explore the fabrication of TMD CFAD using a laser defined ultra thin high K fluorous acid. Firstly, we need to study the performance of these devices on a rigid silicon dioxide substrate and chemically illustrated. Now I would like to know that how, now discussing the image, that there are 4 images A, B, C, D. Now I would like to just give you a little bit of concept of these. Like for image A showing the source, drain and voltage of gate for a molybdenum sulfide field effect transistor with an 8 nanometer oxidized hafnium sulfide film schematically shown in the inside. Image B is showing the forward and the reverse sweep, highlighting a small hysteresis, as you know about the hysteresis curve. And the image C is showing the gate voltage depending on the channel current for molybdenum sulfide FET. Image D is showing the source to drain current and gate leakage current. As you know that the absence of the significant hysteresis highlights the quality and the low impurity contents of our dielectric. And in order to test the suitability of hafnium oxide for flexible application, we prepared a multi-layer molybdenum sulfide field effect transistor. Now I would like to discuss the ReRAM devices. Like, what are ReRAM devices? ReRAM devices are no resistive switching random access memory. They play an important role. They represent a promising emerging memory technology with several advantages over the conventional technology of several group of materials that show resistive switching. Transition metal oxide include fluoroacid, and they are very promising. And they are very different state. We also like to discuss the high resistance state and low resistance state. We like to discuss the set process and reset process. What is the set process and reset process? Set process is a process at 1 volt an abrupt increase in current is observed as a device switch from a high resistance state to low resistance state. And meanwhile, this process is known as set process, and the contrary process is known as reset process. And this is the experimental setup of the ReRAM devices. And image A is showing an example of the switching cycle for the device architecture shown in the bottom right. And image B is showing the first and 100th switching cycle of the same device. Image C is showing the resistance versus cycle number for the two resistance state plotted for the LRS and the HRS. LRS is showing in the blue color, HRS showing in the red color, and the image D is showing the time stability for the two resistive state. And I would like to discuss what are optoelectronic devices. So optoelectronic devices, as discussed below, these are those devices that links with the study and application of electronic devices system that source, detects and controls the light. It is considered as a subfield of photonics, and they play a vital role in the development of nanoelectronic devices. So we also discussed how the creation of the single quantum device is a very important device. This is a experimental setup for the optoelectronic devices. You can see A is showing the current voltage characteristic, B is showing the scanning photos current map, C is showing the normalized photocurrent, D is showing the color map, E is showing the false color change, and F is showing the comparison between the normalized intensity of the EL and PL at the different voltages. So what is the conclusion? So I would like to conclude in a way that we show that ultra-thin hafnium sulfide can be incorporated into a variety of van der Waals heterostructure and selectively transformed into an amorphous high K oxide using layer irradiation. In contrast to sputtering or atomic layer deposition, the use of photooxide hafnium sulfide allows for clean interfaces and without damaging the underlying two-dimensional material. So we can create many devices. These properties allow us to demonstrate several promising high quality of van der Waals heterostructure like ReRAM elements, flexible TMDC, optoelectronic devices, and many others. So what is the future work for these? What is the importance of this work? So I would like to know that with the help of high K dielectric constant, the compatibility with the two-dimensional materials and the ease of laser writing technique will allow for significant scaling improvement and greater device functionality, which we predict to be an important feature for fusible, flexible, semi-transparent van der Waals nano electronics. And if we are helpful in finding the various much more devices of high dielectric constant, that would be very beneficial for us, and then we can make our element much more faster and much more reliable and much more smaller, so that we can take the technology to the next level. That's all for my presentation. I hope that you all liked it. Thank you.